Hello and welcome. In this video, we'll be discussing how we can implement an analysis of variance for a regression model. This is the final statistical test that we'll look at, not accounting for a few confidence intervals. And essentially, this Anova is going to be identical to our previous Anova, except in this case, we're going to be discussing the breakdown of variation in a regression model framework. We talked about the fundamental Anova identity for regression earlier, and just like the fundamental Anova identity formed the breakdown in our Anova chapter, the fundamental Anova identity for regression is going to form the breakdown in this chapter. The tables are going to look exactly the same, so this is going to feel very, very familiar once we discuss calculating the pieces, and even those calculations are going to feel pretty comfortable because they're going to be related to things that we've already found. Actually, we've already calculated all of the pieces we'll need, almost all the hard ones anyway, if we use a little shortcut. All right, so just like before, we had the sum of squares for the model, the sum of squares error, and the sum of squares total, and we used those to make the Anova table. Same thing here. So that fundamental Anova identity for regression has all the pieces that we'd use, just like the fundamental Anova identity did for the earlier Anova analysis. Now, it's important to acknowledge, what does this test? Like, why would we ever do this? And it is worth mentioning that for the simple linear regression, this is a bit of a silly test. So this test is, for the regression case, really just the same thing as doing the test of the slope. So these are going to give the same p-value when we do these tests. But when we get to the multiple linear regression, this test is going to be much more useful. Essentially, what this test does is it tests the contribution of all independent variables in the model simultaneously. And again, with a one independent variable, there's only one. So that's going to be the same thing as just testing the contribution of that one variable, which we already do with our t-test. And so with simple linear regression, again, the f-test and the t-test, they're going to give the exact same p-value. But with multiple linear regression, that does become a little more meaningful. I'll also say in multiple linear regression, there's another fun feature that we can add on to here that's very pragmatically useful. And so we'll discuss that when we get to that chapter. It's also worth noting that we can use the components of Anova for regression to build the R-squared, or the coefficient of determination, that variance explained value. In that, I personally actually quite like the Anova building of the R-squared statistic, and it's because I find the building of that statistic with the Anova components to be much more intuitive in terms of what is R-squared. Remember, R-squared is the proportion of variance explained and the outcome explained by the independent variable of the regression model. And so when we build this, we'll discuss that a little bit. And this is something that I really like about Anova for regression. It's one of, not the only, but one of the reasons we're presenting it here, where the statistical test is identical to our current statistical test for the slope. There's a few reasons we're talking about it Anova for regression right now, but that nice building and intuitive look at R-squared is one of them. So again, we've already have the fundamental Anova identity. We can jump straight to the Anova table. We already talked about in the fundamental Anova identity what are the sum of squares regression, error, and total. All we need is the degrees of freedom. The degrees of freedom for regression is p, the number of independent variables. The degrees of freedom for the error is n minus p minus 1. We've actually already covered that in a previous lecture video. And the degrees of freedom total is n minus 1. The mean squares regression and mean squares error are exactly what you'd think. And the F test statistic is the ratio of mean squared regression divided by mean squared error. From the fundamental Anova identity, SSR is your y hat minus y bar squared and added. SSE is y minus y hat squared and added, and SST is y minus y bar squared and added. So again, this test is for the group of all independent variables to see essentially if they as a group explain things in the outcome. Again, with one independent variable, it's the same as testing the slope. So for the SLR, the simple linear regression case, this is going to be synonymous to beta 1 equals 0 and beta 1 not equal to 0, but only for the simple linear regression case. For the multiple linear regression case, you can think about it testing all of the slopes simultaneously. We're going to compare our test statistic, if we're doing the critical value approach, to a critical value where we have the degrees of freedom for regression as the first degrees of freedom and the degrees of freedom error as the second degrees of freedom. Again, in a simple linear regression, because p is equal to 1 for simple linear regression, this will just be 1 for the degrees of freedom regression and n minus 2 for the degrees of freedom error. Well, the test statistic isn't going to look the same because f and t are different distributions. They are related and the p-values are going to be exact. If you want to find them and you want to make it equivalent, realize that f is the t distribution squared, kind of. So if you take that t test statistic and you square it, you'll get that f test statistic. Just like our normal z, when we squared, we got the chi-squared under certain circumstances. It's worth mentioning the conclusions also match. That is, if you find a significant finding here, you're going to find a significant slope. And if you don't find a significant finding here, you're not going to find a significant slope. It is worth mentioning, though, and I do mention it in the second bullet point above, that the test is always going to be a two-tailed test when done in the when done for the Anova table using the F statistic. In the next chapter, we're going to use variations of this to essentially test groups of variables. So we'll have a group of variables and do a version of an F test to determine, is this group of variables significantly contributing anything in that group above and beyond other groups of variables? We'll discuss when that's useful when we get there, but that's a peek ahead at what we'll be doing. As I mentioned before, the coefficient of determination from the Anova table is pretty straightforward. I quite like it. This is the formula. It is the sum of squares regression over the sum of squares total. And again, think about this. The sum of squares regression essentially serves as the variance due to the regression model, or in a way, the variability explained by x. And the sum of squares total is the measure of the total variability. What this ratio then is literally the variance due to the regression model, or the variance due to x, of the total variability, or the percentage of the total variability explained by x. I like it. It's pretty straightforward to calculate. Once you have your Anova table, you just take the SSR over the SST, so it's really easy, which is kind of handy once you have the Anova table. But the biggest thing I like about this form of the R-squared calculation is that it's so closely tied with its interpretation. It helps you maybe see a little bit more where that interpretation comes from. It's worth mentioning for simple linear regression, again, this gives us exactly the same value as calculating the correlation and squaring it. I will say, though, once we move to multiple linear regression, you can no longer calculate just a correlation and square it. A correlation coefficient, as we've defined it for the purposes of this course, is only between two continuous variables. And so once you have multiple independent variables and one dependent variable, you're not going to be able to do that correlation in the same way. Because of that, this form on this slide is going to be what you end up having to use, the sum of squares regression divided by the sum of squares total, or some analog to this. So this is a little bit more general and can fit for both simple linear regression and multiple linear regression. All right, let's do a couple of examples. So if you have your previous notes, I'm just going to copy and paste from those just like before. Again, we've already calculated almost everything that we're going to do here because especially for inference, we had to find SSE and DFE. Remember to find the MSE, that S squared, and then take the square root of that to get S. That was our starting place for our standard errors in our inference. So we've actually already done a big chunk of this in our previous sections. You're welcome to rework through these by hand if you want. I would start by calculating the sum of squares total, the sum of squares regression, and the sum of squares error, and build up from there. Essentially, that's the same advice as I would give for our general Anova table. Of course, you can always run this in software if you have raw data too. So we already calculated the sum of squares total. That is y minus y bar, y minus the mean of y squared. And this was in our correlation work. That was one of our columns in correlation, y minus y bar squared, and add it all up. We found that to be 13.68. We calculated the entire error row in the regression inference. So remember, we calculated the SSE, we calculated the degrees of freedom E, DFE, MSE. Well, remember that was just S squared, and we calculated that to be 1.5745. But remember, this is super easy with SSE and DFE. The mean squared error is just the sum of squares error divided by the degrees of freedom error. So MSE equals SSE over DFE. So you could just as easily take 7.8726 divided by 5 to recalculate that 1.5745. But we already did that in a previous section, so we can just copy and paste that too. And from here, y'all, we have the sum of squares total. We have the sum of squares error, so we can quickly calculate the sum of squares regression. If you've got two of the pieces, we can pretty easily find the third. All we do is we start with our equation, SST equals SSR plus SSE. We plug in the numbers we know. We subtract 7.8726 from both sides, and we get the sum of squares regression is 5.8074. Ta-da! Now we can go on and build that table. I plug in my sum of squares regression, sum of squares error, and sum of squares total from the previous slide. For my first degrees of freedom, remember that's just the number of independent variables. And in simple linear regression, that's always going to be 1. Error n minus p minus 1 or n minus 2. I have 7 total observations for this data set. That gives me 5 degrees of freedom for the error. And the total, I could add the degrees of freedom together. 1 plus 5 gives me 6. Or I could take the total sample size, 7 minus 1, to get 6. Mean squared error for everything is just the sum of squares of the degrees of freedom. F is the mean squared regression divided by the mean squared error. So that's how I get my F, 5.8074 over 1.5745. With this, I can compare my F value to the critical value. I'm using alpha equals 0.05, putting it all on the top tail. I'm doing 1 and 5 degrees of freedom for the regression and error, respectively. That's what makes the ratio for my F test statistic, and I do the numerator, mean squares regression, over the denominator, mean squares error, as my degrees of freedom 1 and 2. Because my F test statistic, 3.6884, is not bigger than my critical value, again, this is my cutoff, and it's not in that rejection region, it's not bigger than the cutoff, I don't have enough evidence to reject that null hypothesis. Remember, for simple linear regression, null hypothesis is just the slope is 0. That's the null hypothesis. The population slope is 0. So that's my default belief. I didn't have enough evidence to reject that, so I'm sticking with the default belief that the slope is 0. Didn't change my mind. The p-value, well, we can calculate the p-value pretty easily. I mean, if you use the built-in stuff, then that's pretty easy. It's just Anova, and then you give it your regression model. So that's how we do the Anova table in R. And if you're doing this by hand, you do the PF command in R. Again, all of your software has an option to do this at some point. So just calculate it like you normally do in your software. But in this case, it's PF. You give it your test statistic. Degrees of freedom 1 is 1. Degrees of freedom 2 is 5. And then again, we're doing the upper tail. So lower dot tail equals false. All right, now it's your turn. So you are welcome to resolve all this if you prefer, or you're welcome to look back in your notes to get all the components that you need. That'll be good practice, though, in terms of finding all the components that you need and maybe refreshing yourself on how you calculated it all. If you want a deep dive, it's a hard job, no mistake, but it'll be an even better refresher. Try recalculating everything and comparing it to what you had in your notes. See if you can do it. So you remember where it all comes from. Yeah, you're welcome to do that. In either case, pause the video, give this one a shot, and then come back and we'll see how you did. All right. So we have our critical value here, 5.9874. That's our good starting place. Building out the Anova table based on the answers below, this is the table that I get. You can compare your result to this. My F value is very, very, very large. My P value is very, very small. Because my F value is greater than the critical value, we reject the null hypothesis. The null hypothesis was no slope, that is, no relationship between number of students and pizza sales, and we reject that. You said you came in thinking there was no relationship, and now we're changing our mind based on data. So changing our mind from no relationship changes our mind to there is a relationship. So after this, we think there is enough evidence to conclude that there is a relationship. Again, not in the sample, but using the sample data to conclude that there's enough evidence to believe that there's a relationship in the population. As before, when P is really small, we do the less than 0.01 thing. In this case, it's 2 digits. So I'll mention it here. We talked about it in previous lecture sets and videos. With P less than 0.001, you do smaller than whatever you're rounding to. So in this table, I'm rounding to 2 decimal places. So I would do 0.01, the smallest 2 decimal place value, and P is less than that. All right, well, that closes us out for here in our Anova. In the next video, we're going to be talking about prediction. But in any case, in this video, we talked about Anova for regression. We talked about building the Anova table, reminded some of the different pieces in the fundamental Anova identity. All of this was essentially review from our Anova chapter or lecture set where we went through all of the details of Anova, but here we built it up for regression. New information, probably the only new thing that we haven't talked about yet was the degrees of freedom for regression, but everything else you've seen in previous videos in this lecture set. So we just kind of plugged in the pieces and calculated. We did talk about what it is testing and where it's going to be useful, though we admitted in this it's not particularly useful, save maybe as a good way to understand R squared, the coefficient of determination, which we also discussed calculating from an Anova table. All right, team. Well, thanks for sticking with me in this video, and I will look forward to catching you in the next one.